Hello, guys. So let's just very quickly finish off Poisson, see if you have any questions on that. And thereafter, we are going to talk about the famous Russian probabilities people, right? Markov, Chebyshev, and the rest. So let's recall what is a Poisson random variable, guys. It's a very ubiquitous and very useful random variable, in part because it's a great approximation to the binomial distribution. Now you remember, guys, that not any binomial distribution will work. What must be true about the binomial distribution? Can you name a few things? If I want to use Poisson approximation, what should I know about the binomial distribution if I want to use Poisson to approximate it? Large n, small p. Very good. Large number of trials, in other words, lots of opportunity to be successful, but with each opportunity being unlikely. Yes, guys? So I give you, it's like my class, right? I give you a lot of opportunity to do well, but each particular question is extremely challenging, right? So that's going to be the final. You understand what I mean, right? Like, let's say I will have 150 questions on the final, and each of them is going to be so very hard that you are not likely to answer it correctly. Yes, but you will get a good score. So why are you worried, right? Because you have many opportunities. So the expected value will be, how many questions should we have? Maybe I should make, here's a good question. I might do that question for the exam, right? How many questions should we have so that you would have a very good opportunity of success? You know, getting 100, but after answering lots and lots of questions. Good. So this is the derivation which, guys, you should go in by yourself several times. So you understand that if you carry this derivation, you see where did we assume that n is very large, right? And then when we approximate the binomial, the number of successes in the binomial, usually I ask for how many times is, what's the probability that x is equal to k, right? What's the probability of k successes? K successes will be significantly smaller than total number of trials when I do that as well, right? So here, notice when I carry the binomial approximation, k is so much smaller than n. That's used over here, you see, because I'm saying that this fraction and this fraction and this fraction is essentially 1. And for that, k must be very small, which is not a big trouble, because if probability of success is very low, that will make large k unlikely. Do you understand? So probability of success should be very low. Good. And so for instance, half-life, this regularity of exponential decay, it's happening because of Poisson. You might think of it probabilistically, is that you have many atoms within, let's say, a gram of radioactive material, and each atom is extremely unlikely to decay at any given moment. Yes, but because you have so many of them, you have the expected value is going to be just very pronounced, because you have this many experiments, like many atoms, one of them decays. Although on the micro scale everything is so random, on the macro scale everything is extremely well predicted, right? To the extent that you can date material and date it very well. So then we spoke about the expected value of the Poisson. You remember, guys, the expected value of the Poisson should be lambda, because lambda, this parameter lambda, was the product of number of trials times probability of success. So expected value should be very similar to the expected value of the binomial approximated. And the variance should be also very similar to the variance of the binomial, where 1 minus p, the variance of a binomial is n times p times 1 minus p. N times p is your lambda, and 1 minus p is like 1 because p is so small. Yes, guys, so without any calculations, you should know the variance and expected value of Poisson is the parameter lambda. And the parameter lambda is said to be n times p when the Poisson is used as approximation. So far clear, guys? Yes? I mean, I'm stuttering here and there, but you follow me. Yeah? And again, I mentioned that even when the distribution is not Poisson, even where outcomes are dependent, if they're weakly dependent, Poisson is still a good approximation. Of course, it's much harder to analyze and establish rigorously that it is a good approximation, but you can take it for our class to be true. So here is where we calculate expected value and variance of Poisson. Yes, guys? And then we just kind of left at the moment where we're trying to establish some properties of the Poisson random variable, right? So one property, and I think I will skip the proof. Maybe I did it last time, I don't remember. But make sure that you understand it, is that if x is a Poisson and y is another Poisson, and each of them has parameters lambda 1 and lambda 2 respectively, then x plus y, the sum of those variables, will be a Poisson with parameter lambda equal to lambda 1 plus lambda 2. And here we established that we are using the fact that they're independent. And the other theorem is that if x and y are Poisson random variables with parameters lambda 1 and lambda 2, and they are independent, then the probability that x produced k successes is going to have a binomial distribution, given that altogether we had n successes. Yes, so let's quickly just look at that. You see, so we're saying x and y independent Poissons with parameters lambda 1, lambda 2 respectively. Then probability x given y, given x plus y equal to n is distributed, or is a binomial distribution. Okay, so the probability will be, the mass function will be binomially distributed. Why is that the case? Well, let's try to look at it carefully. I think it's a bit obvious, guys, right? So there is some sort of, you see, we already had n successes in total, right? What's the likelihood those successes are due to x, and what's the likelihood they are due to y? Right, so that depends on how likely is the success of x, how likely is the success of y. But each outcome, individual outcome of success, is is independent of the other. So it's very naturally a binomial, I think. So let's see the proof of it. So what we want to establish is what's the probability that x is equal to k, given that x plus y is equal to n. Do you remember that from the previous theorem, x plus y has the distribution of Poisson with parameter lambda 1 plus lambda 2 from the previous theorem, yes? So x plus y is distributed as lambda 1, lambda 2. So what do we get? We get that this is simply the probability that x is equal to k and y is equal to n minus k, because otherwise we don't have the summation. This and that is the intersection of x equal to k and x plus y equal to n, divided by probability that x plus y is n. So what is that, guys? So because they're independent, this is the probability that x equals to k, the probability that y equals n minus k, divided by probability that x plus y equals to n. From previous theorem, we know that the denominator is lambda 1 plus lambda 2 to the power of n divided by n factorial times e to the power of minus lambda 1 minus lambda 2. That's the Poisson distribution of x plus y. For the numerator, we have what? We have e to the power of minus lambda 1, k factorial, sorry, not k factorial, lambda 1 to the power of n, to the power of k, over k factorial times e to the minus lambda 2 to the power of n minus k divided by n minus k factorial. Now you can see which parts here are easily eliminated. So this is crossed out with that. And what are we left with? We are left with just k factorial, n minus k factorial, and lambda 1 plus lambda 2 to the n. So what we get, if I just multiply everything by n factorial, I see here n factorial over a k factorial n minus k factorial. That gives us n choose k. Do you see the formula n choose k here, guys? And then what do I have? Then I can write, I can break lambda 1 plus lambda 2 into a product of power k and power n minus k. So that would be lambda 1 over lambda 1 plus lambda 2 to the power of k times, let me write it smaller. You agree? You see that what I'm doing, guys? So just a mere calculation, which if you think about it, should be obvious. Not tricky, just tricky if you have no sense that this calculation is not necessary, because it's obvious. The result is obvious, right? We had random trials. I mean, we have a bunch of successes. The successes have a sort of weight, right? They have a weight to be, if it, maybe y is more likely, maybe y is less likely, but each trial is independent. If we had n successes, each trial is independent. Again, if you remember, Poisson is like approximation to binomial anyhow. So what do we get? So this is this thing here is p, and this thing here is 1 minus p. So it has a binomial distribution where p is this number. Yes, and we spoke of this exercise last time. I hope you understood it. Unless you have any questions about it, guys, right? So again, just you play around with it, and if you understood that one fact, that Poisson is a good approximation to binomial under special conditions where the number of trials is large and probability of success is small, then you can figure a lot of things out. All right, now guys, let's talk about something that will hopefully be very interesting. So here is just those are estimates for probabilities. They're not always very good estimates, but you can see finally. Remember at the beginning of class we talked about random events being unpredictable in the short run, but very predictable in the long run. So if you take a coin and you toss a coin, you sometimes get heads, sometimes you get tails, right? And then the question is how fast, how many times do you need to throw the coin for the total number of heads divided by total number of trials to approach 1/2? How many times should you do that? when will you see convergence? Right? That's a question that we will be able to answer. Isn't it interesting? We can actually talk about convergence of an indeterminate sequence. Okay, so let's go through it, guys. So Chebyshev inequality is our first step. Oh, sorry, Markov inequality is our first step. And this is what the Markov's inequality tells you. If x is bigger than or equal to 0, is a random variable. In other words, the random variable never takes negative numbers. Then, with certainty, probability that x is bigger than or equal to alpha will be less than or equal to the expected value of x divided by alpha. You understand? So let's say if I know the number, the random variable is alpha is just a number. What's the likelihood? So for example, let's take people, right? I mean, there is not a single person here who is shorter than 0 inches, correct? So let's take all the people measured in inches. That's a random variable that's non-negative. Yes? And let's say the average, I don't actually know inches, so I don't know what's the average height of a person in inches. But let's say, how much is it in inches, guys? You're American. What do you think is a normal? So 100. Oh, good. Centimeters. Thank you, Alan. Right? I agree with you. Inches is ridiculous. Who would use those? So 178 centimeters is the average height of a person. So let's do it in centimeters, right? So then the question is, what's the probability that that a person is bigger than the average by 10 centimeters? Okay, you will see how that 10 is going to be used. The 10 is going to be your alpha. Okay, or if I don't take so the average, let's say 100. Let's say what's the probability in this Markov inequality that a person is 180 is bigger than 182 centimeters. So the probability will be the probability of that will be less than the expected value divided by 182. Do you understand? So if this is 182, and you know the average is 187, no matter what, the probability will be less than 178 divided by 188 or something. You understand what I just said, guys? Or completely with my mumbling, I lost you?
Arkady, can you explain that again?
Yes. So what this is saying is, let's say, just for an example, let's suppose that x is height of a person in centimeters. Okay, so the average is equal apparently to 178 centimeters. The average over human population, I don't know if it's for males or it doesn't matter, right? The average, let's say it's true. The average is 178. If I know the average, then I can, without knowing anything about x, I don't know how it's distributed. I have no idea how the heights are distributed. But I know that the probability of encountering a person that's bigger than, let's say, 188 centimeters is then going to be less than or equal to 178 centimeters divided by 188. That's what Markov's inequality is saying. But even without knowing anything about the distribution, I can be sure that the probability of encountering somebody taller than 188 is going to be this fraction, less than this fraction. You understand? That's the point of the alpha. The alpha is this number that you want x to be larger than.
Gotcha.
Yeah. So now let's prove this this to be the case, guys. Why is it the case? Well, let's begin with this quantity. Alpha times the probability that x is bigger than or equal to alpha is just alpha times the sum of all the probabilities of values that are bigger than alpha. You understand? So I sum all the probabilities over all the values that x can take where x is bigger than or equal to alpha. So far, so good? Now, this is the step, guys. Do you see that xk is bigger than alpha? If I move the alpha over here, it's much better to multiply by xk than by alpha because each xk in my sum is bigger than alpha. Do you agree? Like, let's say I'm multiplying by p of xk, where xk is bigger than or equal to 10. And then next to it is 10. So, okay, so multiplying by the xk, you're at least multiplying by 10 or by bigger numbers. So do you understand this step, guys? So you see this inequality? Alpha, and how I switch it, that's not equal, it's less than or equal. How I switch it to xk times pxk. Yes? And if I switch it to xk times pxk, then this summation looks like the expected value, except I'm not summing over all the values that x can take, but only on those values that x can take that are also bigger than alpha or equal to it. Yes? So then because the variable is positive, if I add the rest of the values, I'm only going to grow the grow this number, right? Making it even larger. So from here to here, there is also an inequality. But what is this? This is the expected value. So you see alpha times this probability is less than the expected value. So if I divide by alpha, you would see that the probability is less than expected value over alpha. Make sure that you understood this claim. Yes? Did you understand what I did, guys? The calculation is very simple, but only, of course, if you understand what is a random variable. It takes a bunch of values. The values it takes are all bigger than 0. Do you see where we use that, guys? We use that at the very last moment. So the values that x take has to be bigger than or equal to 0. Right? Where do we use that? In the last line. Right? So here we have alpha times this probability. Now instead of multiplying each p by alpha, I might multiply the p's by the xk's, because the xk's are at least as large as alpha, and I'm only growing that sum. And because the random variable is not taking negative values, if I then add up all the remaining values, all the remaining xk's, that some of them are smaller than alpha, times the probabilities, I have nothing to lose, I'm just growing. Right? Because xk cannot be negative. You agree? So I'm just growing. It's like, I suppose if you invest in all sorts of stocks, but all the stocks are just going up, none of them are going down. If that were the case, then the more you invest, the better, right? If stocks were always positive, always growing up, then invest all your money, it will grow. Maybe some will grow better, some will grow less. But that's what we use here. X has to be positive here for this to happen. So this means we're going all in. Okay, so that's called Markov inequality. And now we talk about Chebyshev inequality. If x is a random variable with mean mu in variance sigma squared, then for any value k bigger than 0, the probability that x minus mu is bigger than or equal to k is less than sigma squared over k squared. Now, we are using Markov inequality. Look how we are doing it, guys. The probability that absolute value of x minus mu is bigger than k is the same as the probability that the square of absolute value of x minus mu is bigger than the square of k. Yes, we're taking k here to be positive value, so that's nothing is violated if I square those terms. If this is bigger than that, then the square is bigger, and if the square is bigger, then this is true. Yes, same exact statement then. But probability that x minus mu squared is bigger than k, x minus mu squared is the variable variance. It's the variable corresponding to variance, to be precise, right? X minus mu squared is the variable that I average to calculate variance. The expected value of it is the variance of x. Does it make sense? So this is a positive variable, and or non-negative variable, and its expected value, here it is, divided by this number, is by Markov inequality. This probability is less than this quantity, but this quantity is just variance divided by k squared, which is sigma squared over k squared. So that's Chebyshev inequality. We're going to need this inequality, guys, in understanding that very interesting fact. How quickly will we see convergence? How quickly is a random outcome going to become regular? Like throwing a coin. When is the average going to be balanced and not change too much? After how many throws? So what about x minus u is between 0 and 1? What do you mean, Sarah? I'm not following. What is x? You mean minus mu. So x minus mu, you mean, right? Between 0 and 1. What about it? What do you mean by that? So how do you estimate something bigger than, you see? So this inequality tells you if something bigger than a quantity. So x minus mu bigger than a value, and in absolute value, right? And that would be the estimate. That's precisely what Chebyshev inequality is using. And for other statements, maybe it's useful, maybe not. Right? You have to look at the statement. Maybe you can get something, maybe you cannot. We will see in the exercises. Maybe some of it will help. But you understood this calculation, guys, right? So Chebyshev's inequality is just trying to predict what's the likelihood of being bigger than some value. And that depends on the, it would be, so for example, what's the likelihood that your IQ is bigger than the difference between your IQ and the average is bigger than, let's say, 10 points? According to this, without knowing how IQs are distributed, the probability will be less than the expected deviation of IQ scores, that is variance of IQ scores, divided by 10 squared. You understand? That probability will be less than that number, no matter how the IQ scores are distributed. So it's estimating an upper bound for the probability that the variable exceeds a particular number. Good? Or because it's an absolute value, to exceed in this case means to be farther apart, right? So it would say, yeah, whatever. So let me not say more if you understood already. Here is an example, guys. Here is a simple example. So suppose it is known that a bakery produces X number of cakes per day, where X is a random variable with mean 50. So how could such be estimated? Let's say you're running a bakery for several years and you have kept track of how many cakes you produce. Yes, or how much bread you bake, and you find out that on average you bake 50 cakes a day. What can be said about the probability that today over 75 cakes will be produced? So today suddenly over 75 cakes will be produced. Again, guys, we're assuming no change of environment, right? Change of environment already changes distribution, so life is much harder. But assuming that it's a regular day, there's nothing special, you know, just like an average day like the other days, nothing distinguishable about it. What's the probability that more than 75 cakes will be produced? So how do we do that, guys? Well, here we go. Probability that X is bigger than 75. I know nothing about the distribution of X. I don't know how it's distributed. I don't have this information. Yes, but I can at least estimate the following. I can say the probability that X is bigger than 75 is less than or equal to expected value divided by 75. And on average, we have 50 cakes. So that means 50 over 75 or 2/3. So I know that the probability that we will have to bake over 75 cakes is no more than 2/3, maybe much less. But this is universal, but is not always giving you precise measurements. Just telling you there's no way that you will exceed the probability of 2/3 of this happening. Clear? Now suppose that we know also the variance. So the variance is 25. So that means that you know, the deviation is that plus or minus 5 cakes on average are made. Yes. So the question is, what's the probability that today's production will be between 40 and 60? And here I made a mistake. right? But it's kind of like Sarah's question, I think, somewhat like between something and something, yes? So what do we do, guys? So x is now between 40 and 60. That means that x minus 50 is between minus 10 and 10. Do you agree? Do you see why I subtracted 50? Because I want to use the variance. I want to use 25, which means absolute value of x minus 10 is less than 10. That's what this means. Absolute value of x minus 50 is less than 10. And here, guys, is where I make a mistake, because what can we say is the probability that absolute value of x minus 50 is less than, let me consider a different probability. Let me consider the probability that x minus 50 is bigger than or equal to 10. Bigger than or equal to 10. Yeah. So that probability is less than or equal to the variance by Chebyshev inequality. The variance is 25 divided by the number 10 squared, which is 1/4. So that means that the probability that that it's not going to be between 40 and 60 is less than 1/4. Yes, and that means that the probability that I actually care about, the probability that x minus 50 is less than 10, has to be bigger than or equal to 3/4. In other words, the probability that 3/4 likely, at least 3/4 likely, that between 40 and 60 cakes will be made. Good? Whereas the typo, here is where I corrected it. The typo is that I say that this is less than 1/4, but that's wrong. This should be bigger than 3/4. Do you understand why, guys? Because Chebyshev inequality, as anything else, estimates it gives an upper bound for the probability of exceeding something. So here, x minus 50 in absolute value exceeds 10. The probability of that is less than 1/4, which means the probability that x minus 50 is less than 10 is bigger than 3/4. If this is less than 1/4, then the complement has to be at least 3/4. Are you clear? You understood that I made a typo? Even I make a typo, and those typos are you can model by Poisson distribution how frequently that happens. Yes? I write a lot of notes, and the probability of making a mistake is small. So the probability that it's between 40 and 60 is at least 3/4. So it's between 3/4 and 1. Sarah, yes? Because I'm saying probability that x is between 40 and 60 is the same as x minus 50 in absolute value less than 10. And that probability is bigger or equal to 3/4, which means the actual probability is anywhere between 3/4 and 1. But 3/4 is the absolute minimum it can be. Yes? And now we come to the point of it all, guys. This is such an amazing theorem. It's so amazing, right? I just the weak law of large numbers. So here is what the theorem is saying. So let x1, x2, etc., all the way to xn, and it goes n goes to infinity, be a sequence of identical and independently distributed random variables. So they have the same distribution, and they are independent. And the mean, the expected value of each of them is mu. Then for any epsilon bigger than 0, the probability that the average of those random variables minus mu will be bigger than epsilon is going to 0 as n goes to infinity. So in other words, that means that as I calculate the average for more and more of those random variables, the deviation from mu is going to disappear. The probability that you will see a deviation is going to be a very low probability. So let's first prove it, guys. I mean, I'm not sure if that's the best way to approach it, but I'll prove it and then we will try to interpret what the proof means. Agreed? All right, here we go. So first, guys, the expected value, and here it's completely linear. So I factor 1 over n, and that's the sum of the expected values. So this would be 1 over n times mu, which is mu. You agree? So the expected value of the average of those random variables is mu. Now, variance we can calculate very easily because remember, guys, the random variables are independent. If they're independent, covariance is 0. Yeah, they don't vary together, right? Independent means that one goes up, the other does whatever he likes. Covariance is 0. So the variance of the sum is the sum of the variances. So here we go, guys. So the variance is factoring 1 over n makes it 1 over n squared, and then variance of the sum is the sum of the variances. Each of them is variance sigma squared. So we have 1 over n squared times n sigma squared. So the variance is sigma squared divided by n. And so by Chebyshev's inequality, a probability of the absolute value of the average of n random variables minus their average minus mu being bigger than epsilon is less than or equal to sigma squared divided by epsilon squared times n. So how is this theorem useful, guys? Do you understand? I mean, this is a calculation, but can you understand what the calculation is telling you? Let me give you this next example, which will hopefully help. So here is the question. How many times must we toss a fair coin in order to ensure that the sample average of the number of tails is within 1/10 of 1/2? Do you understand what I mean by 99% of the time we perform the experiment? So you can never guarantee anything. Do you agree, guys? Right? I mean, it's not a deterministic sequence. But how many times should you advise that I throw the coin so that I will be sure that I will get 0.5 or any number sort of between 0.4 or 0.5, so 0.4 and 0.6. Yes, guys, you follow me, and I say a few things I said with my malapropisms, but you understand. I want my my average of total tails divided by number of trials to be between 0.4 and 0.6 99% of the time when I perform the experiment. So this is what we are going to then do. So first, each trial can be simulated. Kth trial is xk. It's equal to 1 if kth toss is tail, 0 otherwise. Yes? Good? And 0 otherwise. That's the so then what's the expected value for xk? Clearly, because the coin is fair, the expected value is the probability of getting 1, which is 1/2. It's 1/2 times 1 plus 1/2 times 0, so it's 1/2. And the variance sigma squared is the expected value of xk squared. And this expected value is also 1/2. Squaring this random variable does not change it, right? It stays the same random variable if I square it. Xk squared is xk. So what do we get? We get 1/2 minus this number squared, 1/2 squared, and that's 1/4. So the variance is 1/4. Now, by the weak laws or law of large numbers, what I'm interested in is to know the number n. So I have summed a bunch of, I performed n trials, do you understand? So I suppose I performed n experiments. I tossed the coin n times. Then the average number of tails I obtained is here. And how different is it from the number 1/2? Well, I want to see what's the likelihood it's bigger than 1/10. By the weak law of large numbers, it's going to be the variance, which is variance of x1 through xn over n, and the variance is 1/4 over n. That's the variance. Are you following? Do you see this here? This is the variance, guys. The variance of the sum is the variance of one of them divided by n. This average here is variance of 1 divided by n. So here it is 1/4 from this calculation divided by n. And further divided by epsilon squared, by this number squared. And this number is 1/10. So I divide this by 1/10 squared. Now, if you multiply everything by 100, you get 25 over n. You understand? That means that the variance, guys, this probability, right? So by Chebyshev's, weak law of large numbers, it's a consequence of Chebyshev's inequality. This thing. The probability that I have a deviation, if I perform n tosses, the probability that I have a deviation from that expected probability of 1/2 to be more than 1/10 is going to be 25 over n. So the more I perform, it's going to be less than the number 25 over n. You understand? So, and I want 25 over n to be I want this probability to be definitely less than 100, 1 out of 100. Are you with me, guys? 1 out of 100. So that means what? That means that n is bigger than 2,500. This is what we just figured out. This weak law of large numbers, it guarantees that if you take a fair coin and toss it 2,500 times, then with 99 probability of 99%, in other words, 99 out of 100 times, the number that you will obtain will be something between 0.4 and 0.6. You understand what we just figured out? Isn't it impressive? You understand? I have a way to figure convergence. Right, so if I do it this many times, I can be sure that the number is going to be somewhere between, we can simulate it. Remember, we played it with a computer before, right? I mean, I just don't want to search for the website now, but you can just search for the website and simulate and see what you get, guys. It's a running the experiment. You throw the coin many times. In this case, we can finally say how many times should you do that. Do it 2,500 times. And you will see numbers between 0.4 and 0.6 as the average number of successes over total number of trials. You follow? And that will be 99. Sometimes you would see something very weird. Sometimes you would see an entirely different number, but that will be rare. It will be 1% likely, right? Good. Usually you think that if you say your chances of passing an exam is 99%, usually you feel comfortable, right? So it means that if this test were your exam, in other words, if I were to fail you, if you get some number beyond 0.4 or 0.6, somewhere outside of this interval, you would be still 99% comfortable that you will not fail. Yeah, maybe we should do that because I don't want to grade you. Maybe that's the way we should decide your grade. For each of you, we'll simulate it and see if it's if it's between 0.4 and 0.6. Alan, I hope you're right. You look like you met with a medusa and froze. Good. So You see, guys, so again, how to understand that statement? You might need to throw the coin far less times to achieve that success. It's just, it's a ubiquitous distribution. You understand? You can take the statement to be very, very cautious. Something like, I can claim that 99% of people are less than 14 feet tall. You see, I can claim that if I measure 2,500 people, I will find with 99% likelihood that they are less than 14 feet. You understand? So that's very cautious. You understand? I could have said, well, if I measure 2,000, if I measure 2,500 people, there will be less than 8 feet. Right, most likely, right? 99% of the time, or less than 9 feet. I don't have to go to 14. Clear? So it's just because it's ubiquitous, it should work for all distributions. This does not mean that it's very efficient. It might be that the convergence is more rapid, but it gives you an upper bound on the convergence. Do you have any questions about the weak law of large numbers, guys? Because your mind should be blown. My God, we finally can figure out how to estimate convergence of events that are not determinate, and actually with very easy tools. I mean, these tools are not so sophisticated. Yes, any questions on the weak law of large numbers, or you think you'll have them once we talk about the strong law of large numbers? Right, so I am not gonna bother proving the strong law of large numbers, because if I do, you will just say, yes, we understood, but you will be frozen, transfixed eternally into the screen like fish with unseeing eyes. So let x1, x2, etc. be a sequence of independent and identically distributed random variables, each having mean mu. Then the limit as n goes to infinity of the average will equal mu with probability 1. In other words, what the strong law of large numbers is telling us, guys, is that if I take the coin and I continue in the experiment tossing it and calculating the average, like I did when we introduced chapter 2, if I continue doing that on and on and on, I will eventually see that number 1/2. I will see convergence with absolute certainty, probability 1. Do you understand? That's the strong law of large numbers. In other words, it says that each time we perform the experiment of tossing a coin infinitely many times, if that's even possible, then we will always arrive at the number 1/2. It would always be convergent. The sequence, though it's not deterministic, always converges to 1/2 in the case of the coin. Yes. Whereas the previous statement said that, well, if you look at a certain interval on the table, if you look down the 2,500 row, you would most of the time see a number between 0.4 and 0.6. You sometimes see something else, but most of the time you see a number between 0.4 and 0.6. But it doesn't tell you what happens as you go infinitely down the rows. Yes? That's the difference. So I'm not going to prove it, guys, even though I wrote out the proof, and you can either read it or not. It's another thing. I mean, we didn't study moments, and we are not going to study moments, but that's an interesting topic, moments. Do not think highly of me. It doesn't matter. I've almost quoted something that you would not understand. So quickly, let's talk about the difference between strong and weak law of large numbers. Maybe before I do that, some of you will volunteer. Well, they are related. Yes, they are related to moments of inertia, sure. Expected value, it's like first moment, variance x squared is like second moment, you know. So that's related. So guys, would anybody like, and I would be happy to hear your voice if you want to do that, would anybody care to tell me what you think is the difference between strong and weak law of large numbers? Well, it's too short. Do I need error for week? It's too short, Sarah, but maybe you can give a qualitative type of description. I'll do one slide just below. No, yes, you noticed quite right. Weak is for finite and strong is for infinite. That's kind of going in the right direction. Okay, so let me try to, so Fnu mentioned two important words, finite and infinite. So, right. Yes, so for a long-term result. Yes, so you see, guys, here is the difference, right? So the strong law of large numbers is just telling us that the sequence converges. Right? Remember sequences. You all studied sequences. The sequence converges. But if it's a deterministic sequence, okay, well, maybe, right? But here we have a sequence, and we don't know any of its terms, and yet each time you simulate, the sequence will converge. Do you understand? So the way you should think graphically of the strong law of large numbers is something like this. So imagine that convergence is like this. This place I always love. That's what I always did in school. That's why I was not so frequently in video. I was interested in insects. So I mean, people played soccer, I would just be looking at ants. So many of my examples today are also about ants. So imagine this is an anthill, ant nest, right? So you don't know where the ants are going to come. Yes, but then you begin seeing the trail of ants. One time you do the experiment and you see the trail of ants is like this. But the motion is to the nest. You agree? Then another time you do the experiment and you see the trail of ants appearing in a different place, but it's still going into the nest. Do you see? So I mean, the sequence here is 1, 2, 3, 4, 5, 6, 7, 8. You can even think of taking snapshots, maybe with a fast camera, of a single ant and how it's running into the nest. Each time you release the ant, it's gonna go into the nest by a different pattern. But what's always true with 100% certainty, the ant is going into the nest. That's convergence of an indeterminate sequence. Yes? That's the strong law of large numbers. Now, what is the weak law of large numbers saying? It's saying that if you look at the path of the ant each time it's released, the path of the ant the time it's released seems to very rarely deviate from a particular trail. You understand? So let me now try to draw the weak law of large numbers. Maybe I'll fail. So again, here we have the ant nest. And then here we release an ant, and the ant goes into the nest. Maybe, right? So here is its pathway, and this number is, let's say, this number is n. So I focused on this particular number, right? And then I release another ant. And over here at n, its pathway is very close to the first. And I release another ant. And again, in this region, the pathway is very close, right? They are getting close together at that particular moment. Doesn't talk about the nest. It's just telling me that, roughly speaking, somewhere along the way, somewhere on the entrance of, basically in the sequence of photographs that I take, the first photograph, second, third, fourth, rapidly, right? That I see that starting from some particular photograph, the ant pathways are very close to one another. right? But it does not mean that it's always going to be the case. If I do it many, many times, there might be one, it's still possible. Some ants eventually are very far away, right? So one of them might be entirely deviating this path. You understand? And the difference is very far. It just happens, the further the step, if I take n to be large, the further the step, the less likely you will see this deviation. You would be very unlikely to see the deviation. So truly, the drawing I drew with the green is not quite right. Maybe it should be something like this. That means that it will start going along the same path, but at a much later step. Clear? So strong law of large numbers is talking about the nest. Weak law of large numbers is a sort of Cauchy condition. Do you remember Cauchy, guys? Cauchy sequences. You studied mathematics. So Cauchy sequences are sequences that talk about elements getting close together, right? So if you ever looked at ants, you would very easily understand analysis because you understand what Cauchy sequence, right? Convergence is that they are going after a caterpillar. They converge to the caterpillar or they converge to the nest. Cauchy is this clustering, that the ants are very close together. Good? Cauchy-Schwarz Jack is an inequality, right? Those are two mathematicians, so that's an inequality. Yes, it's a different thing. I said Cauchy sequence. We don't forget Schwarz, of course. Who would forget Schwarz? Well, at it, you should never forget Lipschitz. Every time I pass by a synagogue and it says Lipschitz synagogue, I think, well, they remember. You know the Lipschitz condition, yes? Exactly. Kunya knows. Being Cauchy doesn't, so somebody took analysis. Cauchy doesn't mean convergence, exactly. Precisely. Cauchy is a more general term. Very good, guys. Yeah, but not with me. So it's your loss, of course. You never took analysis with me. That's the best class I ever taught. All right. So guys, here is just this is a sequence. And then I'll try to, in terms of deterministic sequences, illustrate the difference between strong convergence and weak convergence. Because weak law of large numbers is talking about weak convergence. Strong law of large numbers obviously talks about a strong convergence. So this is an example of strong convergence. The sequence is 1 over n. You see, guys, what happens is that this sequence strongly converges to 0. In other words, from one step onwards, you will see essentially no difference from 0. Right? 1 over n is going to be very close to 0. This, on the other hand, guys, is weak convergence. Do you see the sequence is 1 if n is the power of 2 and 0 otherwise? You understand how the sequence looks like? Let me just draw that sequence. So first term is, so we have, the first term is 0. Second term is 2 to the 1. So it's 1. Then we have we could even do a different sequence. We can say instead of that it will be extremely different, extremely divergent. Maybe instead of the one that is drawn over here, maybe a n equal to 2 to the k if for example, basically just look at powers of 2. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and onwards, right? So then if it's a power of 2, I will write the power. So the different sequence from the one I wrote over here. So at 1, let's say at 1 I will write 0. At 2, 2 is 2 to the 1, so I'll write 1. At 3, I'll write 0. At 4, I'll write it's 2 to the 2, so I'll write 2. At 5, I write 0. At 6, I write 0. At 7, I write 0. At 8, I write 3. Yes? So a different sequence from the one I have. Oh, yes, Kunya. No, you want to talk about analysis. That's nice. That's nice. Yes, so Kunyan is throwing you the definition of Cauchy. Right? But let's look here, guys. So 9 is 0. Do you see what's happening, guys? Right? So the 1 is basically it's because 2 is 2 to the power of 1, right? So this is because it's 2 to the 1. And this is because it's 2 to the 2. So I'm using this power, right? So what do you see about the sequence? You essentially will see that there are some numbers that are extremely deviant from 0. No matter how far down you go, there are always going to be numbers extremely deviant from 0. You're going to have 2 to the million, to the trillion. So the sequence will be at some moments extremely deviant from 0, but you're not likely to notice that. You see, because the difference between 2 to squared to cubed is growing larger. So you're going to see many, many zeros, right? So between 2 to the 100 and 2 to the 101, you will see tremendously many zeros, right? Because it's doubling, right? So you see, you have to wait double as far to see the next zero. So that's called weak convergence. In other words, that you see that it doesn't converge, but only very rarely. You see, exceedingly rarely do you see that the sequence is not converging to 0. It's another notion that most likely you did not learn in analysis because it was introduction. It's called weak convergence. Okay, because the sequence for probability it's significant. Okay, so basically, strong law of large numbers tells you that the probability is strongly convergent, and the weak law of large numbers tells you that it is weakly convergent. Okay, every time it's strongly convergent, it would also be weakly convergent, but not vice versa. Something could be weakly convergent but not convergent, just like this example. Right, the sequence does not converge, but it weakly converges. Yes? Wonderful. Any questions about this material? Good. I hope I won't forget my questions for the exam. There's so many to ask, I cannot decide even. And finally, we begin with chapter 5. So we talk about continuous random variables. So how are those variables formed, guys? Imagine doing the following. So imagine that you are looking at how a barber is cutting someone's hair. And here is a hair follicle. Let's just make all the hairs, I'd normalize them or just imagine they're all of length L. And the barber cuts the hair in certain regions. So we have a random variable that describes where the hair is cut. There are a continuum of places where the hair could be cut. You agree? But continuums are difficult to understand because, I mean, well, we want to digitize it, right? Continuum, I believe it's called analog, right? So, I mean, what really happens is analog, but digital means that you break it into either it's here, or it's here, or it's here, right? So then let's grossly break it into 2 regions. So break the hair into half, and every time the cut is made anywhere in here, right, we will say that the cut is made at 0, let's say, and every time it's made over here, we will say the cut is made at 1/2. 0 is the root of the hair. You understand? So it's not true, guys. I mean, right? So this means that I'm having a bad camera. My pixels are not picking too much of a difference. I can only tell if the hair was cut below 1/2 or above 1/2, and I cannot really tell too much, right? So then imagine having watched it, and then I have this histogram. I observe that that 1/2, you see, look at it, right? So this area, I modify the area. 1/2 times 1/2 is 1/4, right? So the area of this histogram represents probability of the hair being cut in that region. You follow what I mean? Not the height, but the area. You can see the height here is this height of the second histogram is bigger than 1. Probability can never exceed 1. Right? So what happens is that, look at it, this is 1/4 and this is 1/2 times 3/2, which is 3/4, right? So 1/4 of the time the hair is cut in between 0 and 1/2, and 3/4 it's cut here. Yes, and then I mean I might take a better camera and I see a bit more pixels. You see, I now divided the hair line into 4 segments. Yes, so this is what happened before, and now when I divide it into 4 segments, I see that that this area, this basically 1/16 of the time the hair was cut here, and then you know, whatever this area is where the hair was cut here, was cut here, was cut here, but the sum of the areas is always equal to 1. Are you with me so far? Right, so the hair is actually cut on a continuum, but here I see only that it was cut in the first quarter, in the second quarter, third quarter, fourth quarter, and I just draw histograms, or I think they're called histograms, right? I draw those bars with the property that their area has to be equal to the probability of the hair being cut there, which I do experimentally. And listen, I just did it many times, and I presume by experiment I'm seeing those histograms. So far, good? And then, guys, look what happens. As I continue creating those bars, as I continue refining it, I get very, very thin bars. You agree? They will start looking like lines. And it's like what happens in Manhattan. There is not a lot of ground, and the skyscrapers get very thin and very long. So then you have the skyline. You see? In this case, the skyline is this green line. Okay, but in general, the skyline could look like this, or like any curve. If the random variable is continuous, that means that the bars are just gradually changing from one to the next. And when they are very thin, you will see a skyline, and that skyline is going to be called the probability density function. You understand? PDF, probability density function, which is this curve. Okay, now in the example I was drawing over here, it looks like, again, I mean, you need to make the bars very, very small to see how it looks like, but it appears that it converges to this linear skyline. Okay, so it appears that maybe the convergence is to the skyline of the form 2x. Where x is between 0 and 1. You understand? No questions, correct, guys? You understood, I mean, why it's intuitive that you would have the skyline, and that's going to be, and then of course, naturally, you see this integral. So the probability that x is between a and b will be the integral from a to b of 2x dx. This is trivially so because of how we constructed the histograms. You understand, the histograms are just so very thin. And all this integral is saying is to add up the histograms that are situated between A and B. Add up the very microscopically thin bars whose height is at any point x is 2x and width is dx. And in this case, it will be b squared minus a squared, and that will give you the probability. So for instance, the probability that this barber cut the hair between 1/4 and 1/2 is the integral from 1/4 to 1/2, 2x dx, which is 1/2 squared minus 1/4 squared, which is 3/16, if I calculate it correctly. You understand, guys, what happened here? So it's completely trivial. If you understand that the integral is just telling you to sum boxes, to add the areas of the boxes, and you realize that what you did here is just you made the boxes very thin. You made it by design. By design, it's integration, because you constructed those bars to be areas. So then all you need to do to find probability, just add the bars corresponding to those areas once they're sufficiently small. And this is going to definition of a continuous random variable. It says to be continuous, guys, if after doing this discrete approximation of this random variable, you will generate a skyline, and the skyline will be a continuous curve. If there exists a continuous density function, such that the probability that x is in the region B is between this number and that number will be the area over the region B and below the curve. Yes? So how do I see a continuous random variable in practice? I suppose, again, I use a very, very fine camera, and I have lots of histograms, and the skyline of those histograms is that supposed continuous curve. So here is, I want to finish with a paradox, guys, the haircut paradox. So let's suppose you go to a barber, and the barber tells you that he cuts hair using the density function f of x equal to 2x, right? Just like I do over there. That's how every hair will be independently cut. So the question is, what is the probability that the cut is made halfway between scalp and the tip? So here we normalize, if the hair is of size 1, if I normalize the hair to be from 0 to 1, in other words, from all of the hair to nothing at 1, what's the probability that the hair is cut at 1/2? So that the hair is cut in the middle. Please answer the question. Simple question, guys. Probability that the hair is cut in the middle. How do you find that probability? Well, I mean, the region is 1/2 to 1/2. So the probability is from 1/2 to 1/2 of 2x dx. 0. What's the probability that the hair is, so it's 0 likely that the hair will be cut exactly in the middle, yes? What's the probability that it will be cut at any point, let's say 7/8 into the scalp, 7/8, close to the tip, like 7/8. What's the probability now? Yeah, 0. Why the rest of you are not answering? Do you see that or not, guys? All right. Do you understand why I'm saying we constructed this random variable in such a way that to figure out what's the probability anywhere is to integrate under the curve. To integrate under the skyline means to add the microscopic bar graphs, which each of them containing area. Do you understand? It has to be something that you get, guys. Very important. So in general, because the integration is 0. So in general, what's the probability that it will be at some number b, where b is between 0 and 1? What's the likelihood that the hair will be cut at b? So are you getting a haircut? I mean, we just verified that the probability of having the haircut anywhere is 0 at any point. Are you getting a haircut? Well, nice to see you, Jack. Are you getting a haircut? Explain if you are or not. Fno says he is not, but he will pay the tip. Guys, I mean, so you look rather confused. First of all, did you understand why integral is the way to go? Yes? I want to see lots of yeses or lots of no's or something if you haven't figured it out. Okay, Sarah says something. Yes, but so that's true. First of all, guys, did you understand my description of the histograms and all of the thing that came before? You understood this procedure? You understood that I built up those bars, and once I do that, I presume that the shape, the skyline, once they become very thin, would look like a curve. So here I presume that they would look like a line, like line y equals 2x. Theoretically, you presume that the shape of the bars will converge to, their outline will converge to some shape, and that shape will be a continuous curve. Yes, and then because they're so small, when I integrate, what do I really do? I add up the areas of those sections. So why is it not surprising that you would get 0, right? So again, I think Sarah says probability equals 0 does not mean it doesn't happen, right? So the thing is, every time the barber cuts your hair, the cut is going to be made in a different point. So the long-term frequency will converge to 0, right? So that's why you can still get a haircut, and yet it's a miracle every time you do, because it will never repeat. The hair will never be cut the same way. Do you understand? So the probability that it will be at B is equal to 0 means that if it happens that the hair is cut at point B, next time you will never see it cut at that point. You might see it cut close to that point, but never at that point exactly. Do you understand? Yes. Again, probability, guys, we talked about it before. Probability is a limit. Limit converges to 0 does not mean that each individual outcome was never a success. The convergence can be 0 even if you had success once or twice or just very rarely. So the way I interpret it is that you will never see a given value repeated, or you will see it repeated so infrequently that it converges to 0. And also, again, you can say that it's very difficult to specify the precise cut, because to say the exact point, well, it depends. If you say it algebraically, then you might need an infinite series. If you just point to it, then you still, how can you point to one location? A point, whenever you point, it's going to create a region. So you say cut at this point, at the point of my pen, but the point of my pen is not a point. It has width, right? So points are very difficult to pick, actually. So maybe one last question, guys. You understand all that, for instance, the probability that your hair is cut between 1/2 and 1/2 plus 10 to the power of -8, for instance, is about 2 times 1/2 times 10 to the -8. So it will be 10 to the -8, which is bigger than 0. So the probability that the hair is cut between 1/2 and a small point thereafter is not so terrible. Yeah, I mean, it's very low, but it's not 0. Now, one last question, guys, is this, you see? So a girl wants to get a haircut. She can go to one of 3 barbers. The barbers cut each individual hair strand in accordance with the following density. Okay, so here is the density. Do you see, guys? Here is barber 1, here is barber 2, and here is barber 3. Which barber do you pick? If you have to pick from those 3, which is your choice? Some people know about this problem, huh? But they made the wrong choice because they picked the wrong distribution. Barber 1, Fiona, okay. Of course, guys, if you pick, maybe you have different preferences for your hair. Okay, so what does this mean? This means, guys, that the barber cuts each hair rather close to its root. So he's going to cut your military style, more or less, right? This barber here is going to trim the hair near the tip. But this barber here cannot really decide what he wants to do. He will sometimes cut it very close to the root, sometimes very close to the tip. So let's draw the beautiful picture of how you would look. So if you begin looking like this, then after barber 1, you look like this. After barber 2, you would look like this. Some hairs are long, some are short. And after barber 3, you more or less look like this, you know, like before. I mean, the point of this exercise is, guys, it doesn't matter. Guys don't really notice. I mean, unless it's extremely long, or, you know, I would not notice, you know. Goodbye. Unless, guys, you want to play what, when, where. I said goodbye and Sarah disappeared, but she forgot there is a what, when, where waiting for us. Yes? What, when, where? Yes. Let's go. Let's see if we win this time.